Okay, this is an analytical solution to a problem involving a pole that weighs 20 kilograms being supported by a person holding a rope which is at an angle of 30 degrees to the pole and 45 degrees the pole makes that angle to the ground. So we're being asked to find out what is the tension in the string or the rope, and secondly, what's the nature and direction of the reaction that happens on the ground. Okay, so let's draw in all the forces first. We're going to have a reaction force coming up here at an angle like this. We don't know what the angle is, and we'll say that this reaction force is called R. First, let's solve for T. So to solve for T with a tension, we can assume that the 20 kilogram mass is evenly distributed around the pole, and therefore it's going to act through its centre of gravity of the pole, which is halfway up the pole. Let's assume too that we're not told how long the pole is, so it's going to be 2 units long. It can be any units, 2 units, so there's 1 unit there and 1 unit there. Doesn't really matter what units they are, just 1 and 1, they're even. Now to solve for T, we're going to use the equations of equilibrium. The equations of equilibrium are that the sum of all the vertical forces is the same as the sum of all the horizontal forces, which is equal to the sum of all the moments, and that has to be 0 for the object to be equilibrium. So all the forces have to balance, the turning forces, the horizontal and vertical forces. Now, these forces, the moments, and the vertical forces and the horizontal forces are not going to be as helpful for us at the moment, because we'd have to resolve R into horizontal vertical components, and we're left with a number of unknowns. But if we take moments, that is a turning force, a force that creates a turning, twisting motion, if we take that about a certain point, we can eliminate one of the forces, which is the unknown force of R. So call this point P here, where the pole hits the ground. If we take moments and try and balance moments about this point, if we keep in mind that a moment is equal to a force multiplied by the perpendicular distance of that force from a pivot point, then, because it creates a turning moment, if we keep that in mind, we can say that the sum of all the moments around about the point P and going in the positive direction clockwise is going to equal to 0. And that will equal to this weight force, which is going to be 200 newtons, because it's 20 kilograms times 10 meters per second, 200 newtons, multiplied by the perpendicular distance of the weight force. And to figure out what that is, this perpendicular distance here, all we need to do is use simple trigonometry. That's going to be a right angle. That's a hypotenuse of 1 unit. This distance here is going to be 1 times cos 45 degrees. So it's going to equal to 200 newtons times, and the moment, which will be in Newton meters, so it'll be 1 times cos 45 degrees, which is just cos 45 degrees. That's the first moment that's produced by the downward weight force. Then counteracted by this another force, which will be the tensile force acting along here. But we need to find out what the perpendicular distance is on that tensile force to the pivot point in order to generate the moment from the tensile force. So there's the tensile force. What is this distance? Well, we've got another right angle triangle, oddly enough, and we know that the hypotenuse is 2 units, 1 and 2, and that's the angle of one of the included angles, 30 degrees. So this distance here is going to be, you guessed it, 2 sine 30 degrees. 2 times sine 30 degrees. And that's because sine of 30 degrees is this distance over 2, and multiplied out, and you get 2 sine 30 degrees. So the tensile force is going to be negative because it's going in an anti-clockwise direction. So it's negative T times 2 sine 30 degrees. Now this is all looking good, and that all equals 0 because the sum of the moments has to equal 0. So let's do some simple maths, bring this across to the other side, and then divide the whole thing by 2 sine 30. So that will mean it'll be t times, I'll just do it for you, 2 sine 30 degrees is going to equal to 200 newtons times cos of 45 degrees. Divide both sides by 2 sine 30, you're going to end up with t equals 200 newtons times cos 45 degrees, all divided by 2 sine of 30 degrees. And t, when you calculate it out, and I've done it before, it equals 141.4 newtons. And the angle of action of t is going to be that this little distance here, this angle. What is this angle? Well, if this is 45 degrees and these two lines are parallel, then this angle, this overall angle here, will also be 45 degrees. Now that's 30, so the difference between the 45 and the 30 is 15 degrees, and that'll be 15 degrees in there. So it's going to be acting like this at 15 degrees to the horizontal. So there's the answer for T, analytically. Now what about R? Well, let's make an assumption and say R is going to act at an angle theta to the horizontal. And now we're going to split R into two vertical and horizontal components, because we really can't solve it with moments. We need to break the forces in vertical and horizontal components to do that. So T is going to be split up, and so is R, because none of them are vertical. No need to do that with the weight force, it is already vertical. So let's say that the horizontal component of R is going to equal to this one here. And again, it's going to make an angle theta. So if I were to reproduce the drawings here, we would say that R makes an angle theta with the horizontal and has components which are going to be equal to, that'll be R cos theta, and this will be R sine theta, the vertical component. By the same token, T is going to be in a very similar boat. T is going to have a force coming down here, and it's going to have an angle of 15 degrees. Let's make it there, 15 degrees. And it'll have vertical and horizontal components looking like this. The horizontal component here, the horizontal component will be, this is T, T cos 15 degrees. And the vertical component will be opposite over hypotenuse, which will be T sine of 15 degrees. Okay, so they're the components of each of these two vectors. Now, given that, let's draw them in. So here's R sine theta, and here's R cos theta. And for the tensile forces, we're going to have this one, which will be T sine theta. And this one here, there's a lot of arrows popping up, aren't there? Which will be T cos of 15 degrees, not theta. So I better fix that up. That's 15 degrees there. Okay, so we've split everything up into horizontal and vertical components. Okay, now let's add them up. So we'll start with the sum of the forces that are vertical, and put that way positive. So looking at them here, we've got them. I might make this a bit smaller so we can see a bit more of a bird's eye view. Yep. Okay. So we can say, summing the vertical forces, we've got, and going upwards is positive, we've got R sine theta. That's the vertical component of the reaction, minus T sine 15 degrees. Yeah. Now also minus 200 newtons equals 0. So, bringing this stuff across the other side, we'll say r sine theta is going to equal to, now we know what T is. It's 141.4 newtons times sine 15 degrees minus, plus, because we moved it across the other side, 200 newtons. And the answer is going to come out in newtons. So r sine theta is going to equal to, do some maths over here, 141.4 times sine of 15 degrees, that equals 36.6, so 36.6 newtons plus 200 newtons, grand total 236.6 newtons, and that's r sine theta. Now we don't know what either r or sine theta is, but if we do the sum of the horizontal forces going this way positive, and that must equal, L must equal to 0, we're going to say that the horizontal forces are, from our diagram up here now, we've got r cos theta, and any other horizontal force really is the one that's at the top here from the tensile, the horizontal component of the tensile force, and that's going to be in the opposite direction, so it's minus T cos 15 degrees is going to equal to 0, because there's only two horizontal components. So we know what T is, it's 141.4, so we can say that r cos theta is going to equal to 141.4 times cos of 15 degrees, and all of that, according to the Ferrel calculator, 141.4 times cos of 15 equals to 136.6. And remember that these are newtons, so the answer will come out in newtons. Now we've got r sine theta and r cos theta. Alright, let's do now, we'll call that equation 1 and call that equation 2, and let's solve. Now, we can say from equation 1, we can say that r is going to equal to 236.6 all divided by sine theta. Now if we plug this into what we know of equation 2, we can say 200, because r now becomes 236.6 times cos theta divided by sine theta, because that's what r is, it's 236.6 divided by sine theta, is going to equal to this 136.6 newtons from here, from 2. Alright. Now cos theta divided by sine theta, well, it's just really 1 over tan. So if we flip the whole thing, well, let's just do this now. So we can say that cos theta divided by sine theta is going to equal to, now divide by sides by 236.6, we'll say 136.6 divided by 236.6 equals to 0.577. Okay, flip the whole thing around so that we can say then tan of theta is going to equal to 1 over 0.577, which is going to equal to 1.73, keeping the 733 really, keeping to 3 decimal places. Okay, and therefore theta is going to equal to tan to the minus 1 of that 1.7333 733, and that equals to, clear all that, so the inverse tan of 1.733, 60.1 degrees, or 60.01 degrees. So that's the answer for theta. Now it's a simple matter now to plug this answer back into any one of equation 1 or equation 2 to derive what r. So let's use equation 1. So we'll say therefore from 1 we could say r is going, the magnitude of r is going to equal to 236.6 newtons, all divided by sine of 60 degrees, or near enough to 60 degrees. Let's do that in maths. So 236.6 divided by sine of 60 gives us 273.2 newtons, and that's the answer to r. So now we know that r equals 273.2 newtons, and it's going to go in the upward direction by 60 degrees like that. So let's just check at that and see what it looks like. We've got a 200 Newton force coming down here, so it's not unreasonable to expect that the reaction would have to be a little bit more, because we've got part of this tensile force pulling downwards, and the reaction would have to compensate for that. So it looks pretty correct. So there's your analytical solution.